For the quiz, let's start with number 1. So the carbon that this arrow is pointing to, this carbon right here, has a hybridization of sp2. And the number of bonds connected to this carbon is 4. So we've got a single bond to the nitrogen, a single bond to the hydrogen, which is not drawn, and we have a double bond or 2 bonds to this other nitrogen. So the total number of bonds is 4, and the formal charge on that carbon is 0. So there's no charge on that carbon. So while we're at it, let's just do a couple more. So if I were to point to this CH3 right here, the hybridization would be sp3, the number of bonds would also be 4, and the formal charge would be 0. If I were to point to this nitrogen right here, the hybridization would also be sp2 hybridized. The number of bonds would be 3, and the formal charge would also be 0. All right, for this, draw the arrow pushing mechanism of the acid-base reaction. So for the caffeine structure, that is our base. And the hydronium cation is our acid. The protonated version of caffeine, or the salt, is our conjugate acid. And the deprotonated version of our hydronium cation is water, which is our conjugate base. Now that wasn't asked for in this question, but sometimes future questions will ask about that. So based on the fact that our conjugate acid has added the hydrogen to this nitrogen right here, this nitrogen was neutral, now it has a positive charge. It did have 3 bonds, now it has 4 bonds. We're going to take this lone pair of electrons, attack that hydrogen, or the acidic proton on our acid, and then these electrons from the bond are going to go to the conjugate base. On our acid, this action had 1 lone pair. Now on our conjugate base, it has 2 lone pairs. Again, on our base, nitrogen had 3 bonds and a lone pair of electrons. Now it has 4 bonds and a positive charge. All right, moving down to the next one, circle the less acidic hydrogen. So the less acidic hydrogen is here. The pKa of this is about 19. If you deprotonate this and put the negative charge in this carbon, that is one of the 2 resonance contributors. For the other resonance contributor, our electrons could move and then push these electrons up, so we'd have another resonance contributor with a negative charge on the oxygen. The more acidic proton is this, so hopefully we can prove that that has something like more resonance contributors, or it's a better atom that the negative charge is on. So we actually have a combination of both in this case. So when you deprotonate this, so let's say we have a base and we use those electrons to take that hydrogen, put our electrons on that carbon right there, then we form the conjugate base of this. Which now we have a lone pair of electrons and a negative charge. So with this, we actually have 2 additional resonance contributors. So we can move these electrons here and push these electrons here to give us this contributor. And now we have a double bond right there. And for our next contributor, we can move these electrons back down, move this double bond over to here, and move these electrons up here. That puts a negative charge on this oxygen, a double bond there. That's now a single bond, and this oxygen is double bonded to that carbon. So here we have 3 resonance contributors, 2 of which we have a negative charge on the oxygen. So this is very similar to the vitamin C example we went over in class, and I would guess the pKa of this, considering it goes right to that carbon, is probably not quite as low as the vitamin C example that we looked at, but it's guaranteed to be lower than 19. All right, for the next one, convert this calculate structure into a bond line structure, including all lone pairs. A lot of you forgot lone pairs on it, so that's a common mistake. And then also I didn't see this bond linear all that much. So drawing this structure, we've got hydrogen triple bonded to a carbon, which is triple bonded. Sorry, we've got hydrogen triple bonded to a carbon, which is triple bonded to another carbon, which is single bonded to a carbon. That carbon has a methyl group on it. And then we've got two CH2 groups. And then after the two CH2 groups, we have our next carbon, which is a carbonyl carbon. And that's attached to a nitrogen, which is an NH2. And that nitrogen has one lone pair of electrons. And this oxygen has two lone pairs of electrons. So this is the answer I was looking for. You could include this hydrogen or not. I'd be fine either way with that. So for the skeletal structure, this is an acidic proton, so there's nothing wrong with showing that. In fact, if you want, it can keep showing as many protons as possible. I have no problem with that for your bond line structures, especially at the beginning of class. Again, the errors that I saw, a lot of people missed the lone pairs on the oxygen, some missed the lone pairs on the nitrogen, and then this wasn't presented as linear quite a few times. So this is 180-degree bond angle here, and 180-degree bond angle on this carbon and this carbon. All right, how many amide functional groups are on this compound? So we have one of those. So our nitrogen bonded to our carbonyl carbon is our amide functional group. We have an imine functional group here, but that's not the same thing. So that should be one. And then for the number of sp2 hybridized carbons, let me go back and erase this. I had a broad range of answers that I saw for this. So for the number of sp2 hybridized carbons, we've got 6 in this ring. So 1, 2, 3, 4, 5, 6. We've got, let me number that. So as I was counting, 1, 2, 3, 4, 5, 6. We've got 7, 8, 9, 10, 11, 12 in this ring. So we've got 2 aromatic rings, one there, 6 each, that's 12. We've got one additional one right here, so that's our 13th one. So that carbon right there, and one additional one right there, so that's our 14th. So we have 14 sp2 hybridized carbons. All right, draw the curved arrow showing proton transfer reaction. So here we've got a negative charge that gives away that this is the base. It's got a lone pair of electrons on that carbon. That lone pair of electrons is going to take that acidic proton. And once we attack that proton, that bond that's holding that hydrogen to what will be the conjugate base is moved onto the oxygen. And that's going to give us our products, which is now propane, and now we have a deprotonated alcohol. So the question is, which side is favored? So the pK of this is about, so very similar to ethanol, let's say 16. The pK of this acid is extremely high, about 60. This is an extremely strong base. This is much more stable than the other. It's definitely going to lean towards this side. So this is the side that's favored. If I'm drawing this, then I'm going to have a tiny arrow going that way and a significant arrow going that way because these are more stable products. All right, for this we've got a carboxylate anion, so a deprotonated carboxylic acid, and we have an alkyne with a hydrogen attached to it. So in this case, if we have our alkyne, that terminal hydrogen has a pKa of 25. I'm going to just draw this. This is definitely our base. This is where our electrons are. So we've got 3 lone pairs of electrons. One of those is going to take that proton. These electrons are going to go to this carbon. And that's going to get us our alkyne that's now deprotonated. We've got a lone pair of electrons on that carbon. And now we have protonated our carboxylate to form a carboxylic acid. So now our oxygen is an OH, and we have our double bond oxygen there. All right, so looking at pKa values, pKa of this alkyne is 25, and the pKa of our carboxylic acid is about 4.8. So this is definitely the weaker acid. This is definitely our more stable conjugate base. This is our stronger base. And this is our, again, weaker acid related to that conjugate base. So that means that in this case, this side is favored. These are more stable than these. So here we've got a weaker acid, more stable base. In this case, we have a stronger base and a much stronger acid. All right, draw all relevant resonance structures using curved arrows. So in this case, looking at our row of sp2 hybridized carbons, we have one here, one here, one here, and one there. And our oxygen is also sp2 hybridized. So that's a good starting point. When we move electrons, we probably want to move them right along this row. We definitely do not want to incorporate this CH3 as that's sp3 hybridized, or anything over here, because those are also sp3 hybridized. So starting out with our electron source, that's always the best place to start. We're going to move our electrons from bond. We're going to move our electrons from atom to bond. We can't stop there because we'd be overfilling this octet. So this carbon has one proton attached. That'd be 5 bonds there. So that means we need to move this double bond from bond to atom. All right, once we do that, now we have a terminal alkene. That double bond there is no longer a double bond, it's a single bond. We have a lone pair of electrons that's sitting on this carbon. That's where our negative charge is. And we still have our single bond to the carbonyl carbon, and then our ethyl group also attached to that carbonyl carbon. So there's our first resonance contributor. And then for our second resonance contributor, we're going to start with a negative charge, move these electrons from atom to bond. We can't stop there because now the carbon here, we've overfilled its octet, so we have to continue moving electrons. So we're going to move electrons from the double bond to the oxygen atom. That gets us to our final resonance contributor, where now we have a double bond there. That carbon-oxygen bond is a single bond. We have a negative charge on the oxygen, and we still have our ethyl group, and we still have our methyl group right there. So of these contributors, for the first we have a negative charge on a carbon. For the second we also have a negative charge on the carbon. For the third we have a negative charge on the oxygen. So this is our strongest contributor because oxygen is more electronegative than carbon.